Today we're going to be talking about functions involving e. And what e is, it's a number that we use frequently in advanced mathematics. The natural base e is an irrational number, so it is irrational, and that means that we can't represent it as a fraction. And it's approached by, or it is defined by this limit, as n gets closer and closer to infinity, it will approach a certain value, which is about 2.718. So when we see e, we need to realize that it is not a variable, it is an actual value, something we can calculate. Now, using the exponent rules from Unit 2, we can treat it the same way. So e to the 6th power times e to the 3rd power, we have two things being multiplied. So we add the exponents. This is going to be e to the 9th power. Okay. This one we can divide 18 by 2 and get 9. And then e, 6 minus 4 is going to be e to the 2nd power. We don't want to calculate what e is. We want to leave it just like this. Then letter C, we distribute that squared to both things. So that's going to be 4 squared, which is 16. E to the 3x times 2 is going to be e to the 6x power. Over here we have the base. We're going to add these exponents. Well, we can't add negative 3 and x. So we're going to take e, add our x's. 1x plus 5x is 6x. And then this minus 3 will just get tagged along because we can't combine those. So it will stay like this. Then this last one, we're going to distribute this. That's going to be 16e to the 6th power over 8e to the 5th. 16 divided by 8 is 2. And then e to the 6th over e to the 5th, we subtract. We get e to the 1st power. But you don't need to write that 1st power. So having that e there, we can treat it like a variable, but we also need to realize that it is not a variable. It is an actual value. So we can do that in our calculator as well. If we were ever asked to evaluate what e is, I have the directions here, second and ln. So remember that second button's up here. And the ln button is right to the left of 4. And you see when you do that, it's e and then has an exponent. So if we're asked to do e to the negative 2, e negative 2, and we get 0.135. When we can stop writing from there. So we're going to do these calculator problems. E to the negative 4th, so second ln negative 4, and we get 0.018. And then we'll do second ln e raised to the 0.36 power, 1.433. Okay. Saying e is an actual value, but we can also treat it as a variable in some instances. So the number of camera phones shipped globally can be modeled by the function. And we have that function there, where x is the number of years since 1997, and y is the number of camera phones shipped in millions. How many phones were shipped in 2007? So we have that function, y equals 1.28 times e to the 1.31x, but we know what x is. We're going to plug in 10, and the reason why we're going to plug in 10 is because it says X is the number of years since 1997, and we're trying to figure out how many were shipped in 2007, which was a 10-year window. So we can type that in the calculator. 1.28, and to get e to some power, we're second ln, and we do 1.31 times 10, all in the exponent, and get that big number there, 625,846.29. So we just type that in the calculator to get our answer. All right, now on the next page, we're going to be graphing functions with e in it. We know that e is approximately 2.7, and since that b value of 2.72 got, so now we're going to graph e functions with a base of e, and our growth rate, or our b value, is e, which is approximately 2.72, and since that number is bigger than 1, this is a growth function. So we're going to graph it the same way, except we're going to have base e instead of base 2, base 3, or whatever we had in those problems. So it's going to look the same as our exponential growth models or graphs. So a is 2. Our b value is e, or 2.72. H is 0. K is 0. Our asymptote in this problem is y equals 0. Our domain is negative infinity, comma infinity. Range is negative infinity, 0, comma infinity. And then with our table, we do 1, 0, 1. And then 1, comma e. But instead of writing e, that's pretty difficult to graph. Let's make it a decimal so we know about where to plot that. And then we'll make that second row and multiply all the y values by 2. So 1 times 2 is 2, and 2.72 times 2 is 5.44. So again, we're just going to guess our best when we do that. So we have 0, comma 2, and then we're going to have 1, comma, was it 5.44? So 1, 2, 3, 4, 5. So about there. And then our asymptote is at y equals 0. So then our graph will look like that. Now the second problem here, we have an invisible 1 as our base, or sorry, it's our a value. We don't have a 1 out in front. Our b value again is e, or 2.72. H is at negative 1 because it says plus 1, and then k is negative 2. Our asymptote is y equals negative 2. Domain is negative infinity, comma infinity. Our range is going to be 0, or sorry, not 0, negative 2, comma infinity. And again, just to make sure, all three of these should match up. Then our table. Now, because our a value is just 1, we don't need to make that third row, but you could. 0, comma 1, and then 1, comma 2.72. Like I said, if you want to make that third row, so we'll go up 0, comma 1. Notice that we're going up by 2's. And then 1 comma 2.7 is about there. Now we're going to move each point left 1 and down 2. Left 1 and down 2. Left 1, down 2. Left 1, down 2. And our asymptote is at y equals -2. So then my graph will look like that. So what I want you to do is to look at this last one over here. Pause the video, try it on your own, and once you're done, unpause it so you can check your answers with mine. All right, so there is your graph and all the information that I was able to pull from the equation. So we had 2 as our a value, and then our base again was e. That 3 plus 3 at the end was our k value, so we went. Okay, so this graph went off our grid a little bit because we had that k value of 3. So everything was shifted up 3, including our asymptote and then all of our points. So that's what it should look like, and that's the information that we were able to pull from the equation. Lastly, but not least, we're going to talk about another compounding interest formula that involves the base e. This looks a little bit like our previous formulas where we had that like 1 plus r over n raised to the nt power, but with using that natural base e, it's a little bit condensed. You only use this formula when you see the word compounding continuously. You use this formula where a is your final amount, p is your principal or starting amount, initial value, and then r is your rate, expressed as a decimal, and t is your time. So it says you deposit $3,500, so that's your initial value, on an account that pays 4% annual interest, so that's 0.04. Compounded continuously means you're going to use that a equals PERT formula, p times e raised to the RT, or PERT. T is 1 year. So we're going to do a equals 3,500 times e raised to the 0.04 times 1 power. And like I said before, we don't need to add that or multiply that 1 in the exponent, but we're going to have some situations where our time is not 1. So I just want you to see where that goes. So we get 3,642. .84. So that would be how much money we have at the end of 1 year. All right, so I want you to try this problem down here. Or that's your initial value. This is your interest. We're compounded continuously, and we're after 3 years. So go ahead, pause the video real quick, try this out on your calculator, and then unpause it to see if we get the same thing. All right, so once we type this into the calculator, we get $5,833.49. Now down here, these are the formulas that we have used so far to calculate exponential growth or decay values. And let's just talk real quickly about when to use which. If you ever see the word continuous, so when to use this PERT formula, when you see the word continuous, that's when you want to use the compounded interest continuously formula, A equals P times E raised to the RT. If we're just compounding interest, you use this formula. So when you see the word compounded, but not continuous. So the way I kind of look at it is I check to see, does it say compounded continuously first? If it does, I know I'd use this formula. If it says compounded any other time frame, I know I use this pink formula up here. Exponential growth model, this 1 plus r raised to the t power, when we see the word grows, like that's the word we're going to associate or increase. If we see the word decay or decrease, that's when we use this a times 1 minus r to the t power. And as I said before, the more you practice this and see these problems mixed in with each other, the better that you'll get at differentiating when to use which formula. So thanks for watching this video. Make sure to like it and subscribe.